This video is going to focus on the concept of calorimetry to kind of get you set up for subsequent videos and then eventually doing the math. So in terms of what we've done in thermochem so far, we started out reviewing Q equals MC delta T, which is how to quantify the energy change when there's a temp change. We then went on to talk about thermochemical equations, which is the amount of heat energy either given off or taken in through a chemical change process. So that's like a potential energy process. So essentially the Q equals MC delta T did a kinetic energy change with change in temp. And the thermochemical equations did the potential energy change with change in bond structure. And what calorimetry problems are problems where we actually look at the whole picture of heat transfer that's occurring. So just like conservation of mass and matter, there's conservation of energy, meaning energy can't be created or destroyed, it's just transferred. So in a scenario where somebody gives off energy, something else will have to take it on. And if something takes on energy, it had to come from somewhere. So calorimetry problems are really just quantifying what's going on with a scenario, given the fact that we have information about both the surroundings and the system. Specifically in chemistry, calorimetry is the idea that we can quantify the energy happening in a reaction by letting heat transfer happening and then measuring a temp change of the surroundings and then kind of back analyzing what's happening because of that. Okay, so if we were in class, we'd use literally like styrofoam cups to insulate our environment, let reactions occur, measure temp change, and by knowing the temp of the surroundings, we can know things about the system. So I'm just going to run through some basic parameters that exist for any kind of calorimetry problem, which will help you with the worksheet of the math. Okay. So in every single problem, I will draw a picture, and I'll draw a picture of both the system, which is always my reaction, and my surroundings, which in a calorimetry problem is always water. Okay, there's other ways to do this, but that's kind of just like the basic setup that most problems kind of use. So given the fact that the system is a reaction, that's going to be our potential energy change, where bonds are being broken and formed, and that's a thermochemical energy process, so that will use the thermostoic math from last lesson. In the water, which is our surroundings, the water is going to undergo a temp change, so essentially a kinetic energy change. So we're going to be quantifying information about the water, always using Q equals MC delta T. So kind of always for calorimetry problems, the system will be a reaction. We'll use thermochemical equations for that. The surroundings will be water with a temp change. We'll use MC delta T for that. So depending on the scenario, there's just a couple main things to keep in mind when you set up these problems. Okay, number one, if the reaction is exothermic, meaning the system is giving off energy, that means however much energy it's giving off, the water is gaining, right? So in these scenarios where the reaction is exothermic, the water will always become hotter because the water is taking in the energy from the system, okay? Always remember that because I'm MC delta T-ing the water, water will be in joules, but the system, because I'm thermochemicaling, totally a word, the system will be in kilojoules. You will have to convert always, but essentially if my reaction gives off, let's say 5 kilojoules of energy, so negative 5 kilojoules, that means my water is taking in 5,000 joules, positive 5,000. So it's just the quick 1,000 conversion to get you from one to the other. Okay. If my system is exothermic also, that means that my potential energy is bigger in my reactants, because essentially from start to finish, energy doesn't change. So total energy on my reactant side equals total energy on my product side. But essentially I have to add in that little heat factor in addition to the chemicals, showing that some of the energy has been released. So exothermic, I have more energy in the reactants because I gave off the energy throughout the course of the reaction. An endothermic system then is just the opposite of all those things. I'm taking in energy, which means my water is actually going to get colder because the water is giving that energy into the reaction, right? So again, MC delta T, but it's going to be getting colder. My reaction's taking that energy in, which means my products will have more energy because it's pulled that energy into the bond structure. And then the same things apply in terms of joules and kilojoules. So if the water gave off, 7,000 joules, that means my system took in 7 kilojoules. Again, a factor of 1,000 for you to consider. So there are tons of different problems that we can solve with these depending on how we set it up. But the main concept here is that Q equals negative Q. So those are the connecting factor between my system and my surroundings that allows me to math things. So if I'm mathing for my water, MC delta T. If I'm mathing for my reaction, I'm doing thermochemical equations. If I'm relating the two, I'm relating them through Q. So there's your basic foundation for calorimetry problems.